You know, the important molecular rearrangement involving the rearrangement to electron deficient carbon atoms are Wagner-Merwin rearrangement, Pinacol-Pinacolone rearrangement, Damjanov rearrangement, benzylic acid rearrangement, Wolff rearrangement, and diene-on-phenol rearrangement. Among these, I have already uploaded videos of Wagner-Merwin rearrangement and benzylic acid rearrangement. Today, I will discuss Pinacol-Pinacolone rearrangement with important examples and their mechanism. Treatment of 1,2-diols, otherwise called Pinacol, with an acid lead to a rearrangement to give a ketone, usually called pinacolone. 1,2-diols are often named as pinacol. Pinacol gets converted to a ketone called pinacolone on treating with acid. And this rearrangement is called Pinacol-Pinacolone rearrangement or Pinacol rearrangement. Right? The mechanism mainly involves the attack of proton to either of the hydroxy group of pinacol to form a more stable carbocation. And as in the case of Wagner-Merwin rearrangement, the 1,2 shift of the migrating group takes place to the electron deficient carbon atom, followed by the rearrangement with the elimination of a proton to form pinacolone. You can see here it is a symmetrical pinacol. You can see both the carbon atom involves two methyl groups, and hence this proton may attack either this hydroxy group or this hydroxy group. And so we will get a protonated pinacol. From this protonated pinacol, a water molecule is eliminated to form this carbocation. It is a stable carbocation, more stable carbocation. It is a tertiary carbocation. And 1,2 migration, as in the case of Wagner-Merwin rearrangement, takes place like this, forming this rearranged cation. And from this cation, a proton is eliminated, forming the pinacolone. This pinacolone is obtained by removing this proton from this rearranged cation. It is similar to Wagner-Merwin rearrangement. A 1,2 shift of migrating group takes place to the electron deficient carbon atom. If we use unsymmetrical pinacol, the proton will attack to those hydroxy group, whereby the elimination of water molecule gives a more stable carbocation. For example, it is an unsymmetrical pinacol. You can see in this carbon atom there are two phenyl group, while this carbon atom involving two hydrogen, and hence it is an unsymmetrical pinacol. And so this hydrogen may attack either this hydroxy group or this hydroxy group. If the proton is attack this hydroxy group, then we will get this protonated pinacol, from which water is eliminated to form this carbocation, but it is less stable carbocation. It is less stable carbocation because it is primary. So this reaction will not take place. But if proton attacks takes place to this OH group, whereby this protonated pinacol is obtained, and by the elimination of water molecule forming this tertiary carbocation. It is a tertiary carbocation. It is primary carbocation, while this is tertiary carbocation. It is more stable, and hence this carbocation or proton attack takes place to form this carbocation, more stable carbocation. And then hydrogen shift, 1,2 hydrogen shift takes place. The rearrangement takes place. Here hydrogen shift takes place to form this aldehyde. Okay. That is how the Pinacol-Pinacolone rearrangement takes place. Okay, it is the mechanism involving Pinacol-Pinacolone rearrangement. Actually, the proton attack takes place to OH group, whereby elimination of water takes place to form a more stable carbocation. That is the driving force for Pinacol-Pinacolone rearrangement. Okay, see this Pinacol-Pinacolone rearrangement. This proton may attack this hydroxy group or this hydroxy group, either of the hydroxy group. Which hydroxy group will be attacked by this proton? That depends on the stability of carbocation thus formed. You can see if proton attack takes place to this hydroxy group, then we will get this protonated pinacol. By removing water, we will get this carbocation. But you can see this carbon, positively charged carbon atom or electron deficient carbon atom, is attached with this electron withdrawing group, an ester group, which is very electron withdrawing or strongly electron withdrawing, and hence this carbocation is less stable. While if this proton attacks this hydroxy group, we will get this carbocation, which is more stable carbocation, formed by the attack of proton to this hydroxy group, and hence a more stable carbocation is formed. And so the reaction follows this path, not this path. So in the next step, phenyl group migrates or 1-2 shift takes place. This phenyl group migrates from this position to this electron deficient carbocation, whereby this rearranged cation is formed, which eliminates a proton, forming the product. It is the product of this reaction. Pinacol rearrangement may be given by a 1,2 diol or maybe a 1,2 amino alcohol, or maybe bromo alcohol, 1,2 bromo alcohol, or an epoxide with suitable reagents such as acid or silver salt or a Lewis acid, boron trifluoride. In all cases, a more stable carbocation is first formed. Rearrangement or 1,2 migration of migrating group takes place with the formation of pinacolone as the end product. So we can say Pinacol rearrangement may be given by a 1,2 diol or amino alcohol or bromo alcohol or an epoxide. In all the cases, first of all, or the driving force for the rearrangement is the formation of more stable carbocation, followed by the rearrangement or 1,2 migration takes place to form pinacolone. In most of the cyclic pinacol, ring expansion takes place by this rearrangement. For example, see this example. Here, ring expansion, this 5-membered ring becomes 6-membered. And so ring expansion takes place by the Pinacol-Pinacolone rearrangement in this 1,2 diol. The mechanism involves first the attack of proton from the acid to the hydroxy group, either of the hydroxy group, because it is a symmetrical pinacol, forming a protonated pinacol. From this, water is eliminated to form a more stable carbocation, followed by the migration of 1,2 migration of methylene group here, from here to this position, or electron deficient carbocation, forming this carbocation, newly formed carbocation, which consists of 6 carbon atom, or the ring expansion takes place here by the migration of these methylene groups to this carbon atom. Ring expansion takes place to form this carbocation, tertiary carbocation. And this rearranged carbocation, from this rearranged carbocation, a proton is eliminated, as we have already discussed, forming the corresponding pinacolone. It is the corresponding pinacolone, or the end product. You can see ring expansion takes place. One of the 5-membered ring becomes 6-membered in the product. And so we can say the cyclic pinacol may undergo ring expansion by the pinacol rearrangement. Okay, a synthetically useful example of pinacol rearrangement reaction is the synthesis of bridged bicyclic compound from a diol. You can see it is a bridged bicyclic compound which is formed from this diol, pinacol, through the Pinacol-Pinacolone rearrangement. By the Pinacol-Pinacolone rearrangement of this diol, we will get this pinacolone. This pinacolone, on reduction with lithium aluminum hydride, this alcohol is formed. This keto group gets, or this carbonyl group gets hydrolyzed, reduced to form this secondary alcohol by the lithium aluminum hydride. And upon treatment with an acid, this protonated alcohol is formed, then eliminates a molecule of water to form this carbocation. Ring expansion takes place by the migration of these methylene groups here, from here to this carbocation. Thereby, this carbocation, tertiary carbocation, is formed. It is a primary carbocation, while when this methylene group migrates from here to this carbocation, we will get a tertiary carbocation, a more stable tertiary carbocation, which is formed from this primary carbocation. Then elimination of proton takes place to form this bicyclic compound, bicyclic alkene. And so it is one of the important application of Pinacol-Pinacolone rearrangement. Okay, that is, bridged bicyclic compounds can be produced by the Pinacol-Pinacolone rearrangement. You know, this rearrangement follows a stereochemical course in which the migrating groups entails trans to the departing group. That is, the reaction occur in an anti-manner. For example, cis 1,2-dimethyl cyclohexane 1,2-diol undergoes a methyl shift to give 2,2-dimethyl cyclohexanone, whereas its trans isomer undergo ring contraction to give 1-acetyl 1-methyl cyclopentane. You can see it is cis-diol. Cis-diol. It is axial and equatorial. 1,2 axial, equatorial is cis. 1,2 axial, equatorial positions are cis position, and so it is referred to as a cis-diol. Cis-diol. It is cis 1,2-dimethyl, cis 1,2-dimethyl cyclohexane 1,2-diol. It undergoes a methyl shift to give 2,2-dimethyl cyclohexanone. On treating with the Lewis acid, Pinacol-Pinacolone rearrangement takes place. See, this methyl group and this eliminating group are anti to each other. Thereby, methyl shift takes place. Methyl shift takes place. It is cis-diol, and this eliminating group and this methyl group are anti to each other. And so, Pinacol-Pinacolone rearrangement takes place by the shifting of these methyl groups from here to here, or 1,2 methyl shift takes place, forming a carbocation, rearranged carbocation, from which a proton is eliminated to form the pinacolone. This pinacolone is obtained as the end product. it is 2,2-dimethyl cyclohexanone. Transdiol, it's trans isomer. It is transdiol. You can see the 1,2 positions, this hydroxy group, this hydroxy group, both the hydroxy groups are axial, and hence it is transdiol. In this transdiol, you will get, see, this methyl group and these groups are not anti to each other, but this methylene group and this leaving group are anti to each other, and hence this methylene group enter to this carbon atom, because this leaving group and this methylene groups are anti to each other. Thereby ring contraction takes place in this Pinacol-Pinacolone rearrangement. Thereby we will get this pinacolone. Ring contraction, it is the 6-membered ring becomes 5-membered ring. Okay, and so we can say the rearrangement follows a stereochemical course in which the migrating groups enters trans to the departing group. That is, the reaction occur in an anti manner. Among the aryl migrating groups, electron donating substituents in the para and meta positions enhances the migrating aptitude, while the substituents in the ortho positions decreases the aptitude of these aryl groups. Whereas electron withdrawing substituents in all the position, maybe ortho, para or meta, in all these positions reduces the migratory ability of the aryl group. See here, para-methoxy phenyl group having highest migratory aptitude, and then comes para-methyl phenyl group, then meta-methyl phenyl group, then phenyl group, then chlorophenyl group, para-chlorophenyl group, then ortho-methoxy phenyl group. Here ortho-methoxy phenyl group having least migratory aptitude, because this ortho-methoxy group exhibit a steric strain or steric hindrance to the migrating group for the attack of electron deficient carbon atom. Among the phenyl group, methyl group and hydrogen, the migratory aptitude normally decreases from phenyl to hydrogen. Phenyl greater than methyl, greater than hydrogen. Okay, see this example. You can see which hydroxy group among this pinacol gets protonated. Either this or this. This carbon atom consists of two phenyl groups. One is attached with a para-nitro group having minus M effect or electron withdrawing effect, while the other phenyl group having a para-methoxy group having plus M effect or electron releasing effect. See this carbon atom containing two methyl group having plus I effect or inductive effect or electron releasing effect. When this hydroxy group is protonated, leading to the formation of a carbocation having a phenyl group with para-nitro group and electron withdrawing group. Whereas if this hydroxy group of this carbon atom is protonated, the carbocation formed will be stabilized by this two methyl group having electron releasing plus inductive effect. And so naturally this hydroxy groups gets protonated to form corresponding carbocation by the elimination of water. You can see the mechanism here. This hydroxy group will be protonated first to form this protonated pinacol, and by eliminating a molecule of water, it gives this more stable carbocation. Then here a question comes, which of the phenyl group will migrate, either this or this? This para-nitrophenyl group is having minus M effect or electron withdrawing effect, and this para-methoxyphenyl group having electron releasing plus M effect. Usually more electron releasing group will be having greater migratory aptitude than the other. Then here the para-methoxyphenyl group gets migrated from this carbon atom to this carbocation, thereby forming this rearranged carbocation. And from this carbocation, a proton is eliminated, forming this pinacolone. Okay, it is the end product. With this discussion, I conclude this video. Thank you so much for watching. Thank you.